Hello there, and welcome to this collection of notebooks and tutorials on multi-rate signal processing. This is a course offered by Professor Schuller at the UMNL University of Technology. I am Renato, the instructor for these online materials, and on this tutorial we will talk about low delay filter banks. So let's get started. Last time we saw that an MDCT type filter bank leads to an algorithmic delay of z to the power of -1 in the lower sampling rate, hence a delay of one block over the analysis and also synthesis filter bank. Remember, the z to the power of -1 came from making the inverse delay matrix d of z causal. In addition to this one block, we usually need to take into account the so-called blocking delay, which results from assembling our incoming samples into blocks of length n. We first have to wait for n-1 incoming samples on the analysis side, and at the arrival of the nth sample, the block is full, and we can send it immediately to further processing. Hence, the blocking delay is n-1 samples. Observe that we have no blocking delay on the synthesis side. This means that the total delay is both this blocking delay plus the delay resulting from our matrices. In the case of our MDCT type filter bank, the total delay, or so-called the system delay, is our blocking delay of n-1 samples plus one block delay from the polyphase matrices, and is given by here, the ND. So it's our blocking delay of n-1 plus one block delay from the polyphase matrices. So we also have the length of our filter, L equals to 2n, which results in the system delay to be the length of the filters minus 1. This relation holds in general for para-unitary filter banks. Observe that mathematically it only makes sense to define a delay over the entire analysis and synthesis filter bank, because here we have the exact same signal as the input signal, just delay. After only the analysis, we only have sub-band signals, which look differently and have a different sampling rate. Hence, here we cannot really define a delay. For para-unitary filter banks, the only possibility to reduce the system delay is to reduce the filter length. But this also degrades the filter characteristics. For instance, it would lead to reduced stop-band attenuation. Often in applications like real-time audio communications, it is desirable to have a lower end-to-end delay, but also good filters with high stop-band attenuation, such that we will still obtain a good coding or compression performance. There, the solution are the so-called low-delay filter banks. With them, it is possible to reduce the system delay without reducing the filter length L. And how does this work? Or first, how do we get longer filters than the MDCT type filter banks in the first place? For MDCT type filter banks, we only had filters of length L equals to 2n. So how do we make them longer? To see a solution, we first need to take a look at the polyphase matrix again, this time for filters of arbitrary length, so more than 2 times n. We again compute our folding matrix of it using this equation here, so Fa times d of c equals to h of c times t to the power of -1. As for the MDCT type filter banks, just that now our analysis polyphase matrix h of z can contain baseband impulse responses h of n, a of n, with arbitrary length L, and L can be much larger than 2 times n here. So the resulting form of our analysis folding matrix is the same as for the MDCT type filter banks, but with higher degree polynomials in it as expected. So here we have our analysis folding matrix. We still have the diamond shape, and here we have h n downsampled given by this equation here. So we have 1 and 2, which are the z transforms of the downsampled by 2 versions of our baseband prototype h of a. And here we have the Z transforms for the analysis at phase n. And the minus sign in minus Z to the power of 2 results from our cosine modulation function, changing its sign every second block. So here these equations, they are from these transactions on signal processing from Professor Schuller, new framework for perfect reconstruction filter banks. So observe that this FA of Z corresponds to our FA times D of Z. And observe that the order of the polyphase polynomials determines the resulting filter length of our filter bank. If the highest exponent is m, then our filters have length m plus 1 blocks of 2 times n here, since we have a downsampling of 2 times capital N, or the length of m minus 1 times 2 times capital N. Here we can observe two effects. One is that the shape of our analysis folding matrix has again the diamond shape, as seen before. And second, that the polynomials in it now have a higher order depending on the length of our filters. For the MDCT type with L equals to 2 times n, we still get an easy solution here. But what about longer filters? Our goal is still to obtain a perfect reconstruction and also to obtain finite impulse response filters for our synthesis to make it easier to handle. The approach now is to use our previous matrix decomposition, writing our polyphase matrices as a product of simpler matrices, and simply extend this product with additional matrices such that we keep the diamond shape of our resulting folding matrix intact, because this was the result of our cosine modulation, which we would like to keep it intact, such that we increase the polynomial order and hence the resulting filter length, such that we get easy FIR inverses, and such that we can control the resulting system delay. The trick now is to invent additional matrices which fulfill these requirements. These additional matrices can be split into separate types. The first type is the so-called zero delay matrix, which is given here. It has an inverse, which is already causal, so we don't need a delay to make it causal. So here is the inverse. So in Sympy, we can create this matrix. So I'm importing from Sympy everything from NumPy, then I'm creating the symbols for Z. I'm creating symbols for the coefficients E. So this coefficients E here. And then we're having our zero delay matrix, which indeed, if we see here, is identical to this one here. And we obtain the inverse by making e to the power of minus 1, and then we have the inverse, and we see that this is indeed the form as above. We can now multiply our analysis polyphase folding matrix 1 to the analysis folding matrix 1 with the zero delay matrix and get polynomials of higher order, because we have elements with z to the power of minus 1 in it. The synthesis polyphase matrix is multiplied by this inverse to still obtain perfect reconstruction. Since the inverse also has polynomials of degree 1, it is still FIR. Also, since the inverse is already causal, we don't need any multiplication with z to the power of minus 1 to make it causal, and hence no additional delay. This means if we use this matrix, we can increase the filter length but don't increase the delay. In principle, we can repeat this process as often as we like and get arbitrarily a high filter length but no increase in delay. So zero delay matrices increase the filter block length by 1 block but don't increase the system delay. We will increase the filter length by 1 block because the increase of the order of the polynomials by 1, which corresponds to 1 block. There is a second type of matrix with the same properties where we simply use the other half of the diagonal. And we have it here. It's causal and inverse is given here. So contrary to diagonal matrices where we need to take the inverse of each element of the diagonal, here we obtain the inverse by flipping the diagonal half and by flipping just the sign, which keeps it causal. So we are flipping the sign and we are flipping the diagonal half. Let's take a look at a Python Sympy example. We would like to see how the product P of A of C is equal to FA times D of C times G of Z of our folding matrix FA of C with the zero delay matrix G of Z look like. So here I'm importing Sympy, I'm defining symbols for Z, symbols for G, and symbols for H. Here's our FA matrix, here's the D matrix, here's the G matrix. So we're just printing them here. And here we have the multiplication of FA times D times G. It's given here. And we can see that this is indeed the diamond-shaped form of equation 1. But when we compare it with equation 1, we could now read out the resulting final baseband prototype filter for the analysis H of A. Observe that equation 1 is for an even number of zero delay matrices. For odd numbers, as in this example, we would need to flip the matrix in equation 1 horizontally. So we'll flip left to right. So now we don't specify H of A in our design process, but we start with our coefficients for our matrices and obtain a baseband prototype filter H of A with the desired length and delay properties. What is a possible drawback of these zero delay matrices? If we only increase the filter length with our zero delay matrices, we can observe that the far-off attenuation increases easily, a clear improvement over the MBCT case. But the nearby attenuation to the neighboring subbands increase not as much as for orthogonal filter banks with similar length but with more delay. Hence, it can make sense to also increase the system delay to obtain filters with higher nearby attenuation more easily. This leads us to a matrix which is very efficient in increasing the system delay, the opposite of zero delay matrices. The so-called maximum delay matrices. They basically result from exchanging z to the power of minus 1 by z in our zero delay matrices and a multiplication with z to the power of minus 1 to make them causal. So this is what we are doing here. This is one type of matrix. Each matrix in our cascade has its own coefficients. The other type is given here. Their inverse need a multiplication with z to the power of minus 2 to make it causal, and is correspondingly this one here and this one here with the multiplication of z to the power of minus 2. Here we can see that the matrix and its inverse leads to n blocks of delay. So we have here and here. Observe that the maximum delay matrices have a polynomial order of 1, just like the zero delay matrices, and hence increases the filter length by 1 block, but increase the delay by 2 blocks. This is twice as much as for an orthogonal filter bank. Using only maximum delay matrices would result in similar frequency responses as with only zero delay matrices. The impulse response would only appear time reversed. We get increased nearby attenuation only if we mix both types of matrices. Orthogonal filter banks can be obtained if we use the same number of maximum delay and zero delay matrices. Our resulting polyphase matrix for the analysis then becomes this product, given here, where H of M is either the H1 of Z if P is even, or H2 of Z if P is odd. For the synthesis polyphase matrix, we get the inverse product, and the result is given here. Now we can design the impulse response length and the system delay of our filter bank. The total number of our zero delay and maximum delay matrices determines the length of our impulse response, including the effect of the Fa times Z of Z matrix, a length of n blocks, and we obtain a total filter length equals to L equals to 2 plus Q plus P times n. And just the number of maximum delay matrices Hm of C determines the system delay, including the effects of the matrix multiplication Fa times d to the power of C, and the blocking delay with a delay of 2 times capital N minus 1, and we obtain a system delay equals to ND with 2 times N minus 1 plus 2 times Q times N. Each zero delay and maximum delay matrix increases the impulse response length by one block of n samples, and each maximum delay matrix increases the system delay by n blocks, so 2 times n samples. In this case, starting with the MDCT delay of 2 times capital N minus 1 samples. It is also possible to start with a lower delay than an MDCT by setting the leading samples of the MDCT type part to 0. Observe that we obtain the same analysis and synthesis baseband impulse response if the determinants of our submatrix of our polyphase matrix are equal to minus 1 as seen before. If we look at the zero delay matrices, we find that the determinant of the submatrices is already equal to minus 1, and it's very practical. If we look at the maximum delay matrices, we see that their determinant of the submatrices is minus z to the power of minus 2, which is their resulting delay contribution, and a factor of minus 1, which has the same effect of leading to the same analysis and synthesis impulse responses. All we need to do now is to make sure that the matrix Fa has a determinant of minus 1 in their submatrices to obtain identical analysis and synthesis baseband impulse responses. This means that the number of unknown coefficients for the folding matrix Fa is going down from 2 times capital N to 2 times capital N minus capital N divided by 2. So the remaining capital N divided by 2 coefficients come out of the determinant equals to minus 1 condition. This also makes the design easier because then we only need to optimize one side of our filter bank. For instance, the analysis side, and we have a reduced number of coefficients. We need a numerical optimization because we now have a long cascade of product with many unknown coefficients in the Fa folding matrix, the zero delay and the maximum delay matrices. We need to optimize them such that we obtain a good frequency response for the resulting impulse response. We can use equation 1 in this lecture and our product for the folding matrix FALC without the transform matrix T to read out the resulting baseband impulse response HA of n. We can then compute the resulting frequency response and use that as a function to optimize towards some optimum frequency response, for instance an ideal low-pass filter as the prototype. An example application of this type of filter bank is the audio coder enhanced low delay AAC in MPEG 4, and here it is used to obtain a lower encoding and decoding delay. For low delay filter banks, it is useful to process the samples as they come from the sound card. Hence, we need a different implementation, an implementation which is not based on the signal already in memory. To obtain it, we interpret the z to the power of minus 1 as a delay by one sample and implement it using a memory element which stores or delays samples for one sampling interval. So the delay matrix D of Z, for instance, can be implemented as follows in Python. We will now take a look at a real-time MDCT or low delay filter bank implementation producing a waterfall spectrogram including the synthesis filter bank and playback of the reconstructed signal. For that, we are going to use NumPy, SciPy signal, PyAudio, and just IPy widgets, so some controls of the GUI. We are going to use CV2 this time, OpenCV, to plot our spectrogram. Here we are defining some signal processing parameters such as the number of subbands and the block size, the number of audio channels, the sampling rate, and here are some parameters to plot our spectrogram. At this point we are defining our D of C matrix. Here is the inverse of D of C matrix. Here is the F matrix. Here's the inverse F matrix, and here is the DCT4 transform, and here is the complete MDCT analysis. So the inverse MDCT is the synthesis, and we have here. So here we have all the elements required to have a complete MDCT analysis and synthesis filter banks. Here I'm just defining a GUI so we can control our spectrogram start and stop. I'm running on a separate thread so we can have the PyAudio working with audio, OpenCV working with image, and we can still access our buttons. So here is the function to plot the DCT. So as usual, we read the audio input stream into data with blocks of length equals to chunk size. Here we will shift a frame up for our spectrogram. Here is the analysis MDCT of the input. Here we can do some processing if we want. Here we are defining for our waterfall color mapping, and we are defining our frames for our OpenCV. Here we are displaying the frames. Then we are taking the inverse or the synthesis MDCT to get the reconstructed signal, and then we write the samples as audio stream. And here when we stop the OpenCV, we want to release the capture. So here is just a thread that I'm running this function here. And here we will start the audio, and here we will display the buttons to start. So now if I start, hello, we have here our MDCT spectrogram. And then we stop, and this is our demo.